So, for yesterday in class, hi Warner, hello. We saw Warner's video.
Let's go, Warner.
Wait, he's Skyping right now?
No, but I'm making a video for him. He's gonna watch later.
So I thought he was in.
Taco.
He's in like South Africa.
Right.
Yeah.
So you can watch a video from South Africa.
Aren't they doing that?
Oh my god. What? Are they doing?
I mean,
What is it?
they're doing math, but they're doing things differently. So he doesn't fall so far behind our class. We're following along. So, I mean, he is doing that, but it's much different than what we're up to. Okay, so homework last night was just playing around with the trig identity some more and showing how to get side A to equal side B. Okay, how to verify the identities. All right. Before we begin, I want to go ahead and remind you all, rewrite up kind of the rules for going about doing this. Okay. So, rules for solving trig problems. Okay. The first rule, all right, is that you want to start with one side of the equation at a time. Side, and pick the most complicated side. Side. Okay? It's far better just to do one side, okay, not to try to do both sides at once. Now, sometimes you have no choice, you have to work both sides, but try to start with just one side, and the side you pick, start with the most complicated side, okay, and whittle it down basically, okay? 2, look for opportunities to factor, simplify, do algebra stuff, etc. Algebra stuff, very technical term there, okay? Basically, yeah, so like, you know, if I see like things, you know, if I have two fractions, get a common denominator, okay? If I've got something that's common throughout, factor it out, okay? You know, but basically, if something's like complex, simplify it down, okay? But look for things to do that sort of thing, okay? Basically, 3, use the identities, okay? Remember that sine pairs with cosine, tangent with secant, and cotangent with cosecant. Okay? All those things pair very, 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 very nicely together. Okay? And the fourth and final one, okay, when all else fails, convert everything into sine and cosine. Okay? So if you basically run into a wall, you can't figure out what's going on, you don't know how to get side A to equal side B, just get really angry, throw everything down and say, screw this all, it's time to make it all sides and cosines. And then go from there. Okay? Got it? Okay, so again, these are your kind of list of things. Again, I wrote this list up yesterday, so you had a list kind of like this one from yesterday. But this goes through again and just kind of lays out what we do when we work these things out. Okay, we're just going to follow along with these steps. Okay, so what we're going to do now, okay, is look at homework problems from last night and see how these conversions work. Okay, So our first one was, hang on, all my faces here. How about that? Over here. All right. So, just take these down fast. Okay. So some of this is two different homework assignments that got put together. So, all right, 1 through 9 on page 365. Okay. What we're going to do here is we're just going to verify the identity. That is, make each side equal to each other. And these are the easy ones. Okay. These are kind of the practice ones. So our first one up here is that we've got the sine of t, cosecant of t, and we're saying that's equal to 1. Okay? Now, the fact that it's t instead of x or theta, does that matter? No. It's going to work just the same way. Okay? But what would I do to show that these things both sides are equal? This one's fairly simple. Yes?
Make the cosine 1 over sine.
Yeah. So I'm going to take the cosecant and make it 1 over sine. Okay? And obviously, if I multiply something by its reciprocal, what do I get? 1. So this would be good enough to stop right there, but if you wanted to just write 1 equals 1, that's cool. Okay? So of course we do. Okay? But that's the sort of idea that we're doing here. We're just kind of taking things and whittling them down. Okay? Let's look at number 3. Okay? Similar sort of idea. Okay? We have cosecant squared of x over the cotangent of x, and that's equal to the cosecant of x times the secant of x. Okay? Now, before we go any further here, what's the rule say? I'm going to pick one side, right?
Yep.
Pick one side to start with. What else does that first rule say? Pick the harder side, the more complex side. Which is the harder, more complex side here?
Left.
The left side, because it's got that cosecant squared at the top, right?
Yeah.
So we're going to try to make this side, we're trying to show that this one equals this one here, okay? So, first thing I'm going to do is, well, over here I've got cosecants and secants. Here I have a cosecant and cotangent. So what should I probably do to that cotangent? Yeah, use an identity and change it into cosecants and and secants, right?
Mm-hmm.
And the identity then, if you remember, was that the cotangent is equal to the cosecant over the secant, okay? So I can rewrite this as the cosecant squared of x divided by the cosecant of x over the cotangent, over the secant
Ooh, I look a little more
of x.
harder.
Okay? Now what can I do? What happens to my cosecants?
Cancel.
Yeah, one of them cancels out, right?
Oh, wow.
This guy goes away, knocks off the square,
That guy's
and then what's going to happen to the secant? It's going to stay down there? I'm dividing this by a fraction so it goes up, right?
Mm-hmm.
So we can rewrite that then as the cosecant. Oh, go away, email. Shoot. I bring the secant upstairs as a secant of x times the cosecant of x. And is that equal to cosecant of x, secant of x? Those two things equal? It looks like they're equal. They're equal. Okay. We don't have to be silly. They're equal. Okay. So that's how these things work. Any questions there?
What ID did you use for making cosine? Was that a...
That was the one of the quotient identities. Okay.
Quotient,
So
sorry.
remember the ones that are kind of listed in the book
Yeah.
is that the tangent's sine over cosine, and the cotangent's cosine over sine. Okay. But there's also versions with secant and cosecant. So like the tangent is secant over cosecant, and the cotangent is cosecant over secant. Okay? So kind of keep that in mind, okay? So that's the identity I use. If I had trouble seeing all that too, what would be my fail-safe?
Make it all sine.
make it all sines and cosines, and then I'd easily see what's going on there. Okay? All right, good. All right, let's see. Let's look at number 5 here. Okay. We've got the cosine squared of beta, okay, minus the sine squared of beta equals 1 minus 2 sine squared of beta. All right, who wants to take this one? Can I get a volunteer?
This is a different language.
Is the Greek letter beta throwing you off?
Yes.
It's just B. If you want to, just make it a capital B.
Could you start by changing the left side to 1 over secant squared b minus 1 over cosecant squared b?
No,
Okay.
you can't do that.
Or
I could, but do you think I really want to do that?
No, that's...
Not really. Okay. Carl, you got your hand up?
If you just move the 2 sine squared b at beta, you get like the Pythagorean quotient.
Ah,
or whatever.
okay. So what you recognize immediately is that, hey, remember, these things ultimately
recognize it.
work by algebra, okay? So the question, we always start with the first question, which is the more complex side? In this case, quite frankly, both sides are equally as complex. Because I got cosine squared and sine squared on this side, and while I have a 1 on this side, I also have a 2 sine squared beta. We don't like 2's, okay, when we're doing these things, okay? We absolutely hate 2's, okay? We're doing trick stuff. So basically, like Carl, I would probably start on that side and say, okay, let's get rid of that 2 as fast as possible. Now, the only way we could do that is with algebra, by just simply shuffling everything around, okay? Just because these things are trick doesn't mean they don't follow the rules of algebra when it comes to an equation. So let's add 2 sine of beta squared to both sides. Okay? And if I do that, okay, those will go away, and over here I'm going to have the cosine squared of beta plus the sine squared of beta is equal to 1. And do I actually need to go any further than that?
Nope.
Nope, because this is what?
Pythagorean.
This is just the Pythagorean identity at this point. Okay. So maybe just throw a note that it's actually the Pythagorean identity and get the idea. Okay? So again, shuffling things around. Okay? Alright. Let's pop words. It's 7 and 9. What do they look like?
7.
Oh! 7, we have a 6 and a 5. Do we like 6s and 5s?
no.
Nope. However, what can I do to the 5? I can shuffle it over, right? And then I have just tangent squared plus 1 equals secant squared, and that's a Pythagorean identity. Okay, good. And 9, I have 1 plus the sine squared times 1 minus the sine squared equals cosine squared. So let's take a look at that one real fast. All right. So with one like this one, what do you think I ought to do? I should actually multiply it out, right? FOIL method it. I don't even have to be like super foily with this one, because that's the difference of when I multiply that, I'm multiplying something by its
Just
conjugate.
sine x squared.
So it's just a sine squared, yeah, sine squared of x. So 1 times 1 is 1 squared minus sine squared of x equals cosine squared of x. Okay? And what can I do?
Add sine squared.
Add sine squared to both sides. Shuffle things around. Every day I'm shuffling. There we go. Okay? And that's it. That's all you have to do. Okay? It's true. Every day in math I'm shuffling. So,
Yeah.
alright. Any questions on how these things work? Okay? These are fairly easy ones, because there's really just one step or one trick that you're using. These can get much more difficult, which is what the second half, the 39, 41, 42, and 44 are all about. Okay? So let's take a look at 32 to start with. Okay? Since we can do these in order. Okay? This is how it looks. Okay? So 32. Now, I know how to do 32. So I want you all to kind of walk through and figure out how do I get these things to look correct. Okay?
But
Okay? So, that's what we got there. Okay? Oh, what?
Wait.
Ah.
Isn't it 30 now?
No, I'm doing 32 first. We have 39, 41, 32, and 44. They're all on the same page. Hang on one second. Let's fix this. The book misprint here. Now it's doable. Okay. Well, who has an idea?
Multiply everything by tangent over x.
No, you-
Okay, I can multiply everything by the tangent. Not sure that helps
Yeah,
me very much.
if you did that, it would cancel the denominator, and then you just have tangent x equals 1 or 0 or something like that on the other side.
Okay, so okay, I guess that would work. Yeah, well, sort of work. Hang on. Think.
Or factor.
Not necessarily a factor, but what can I do when I add two things, when I have two things added together in a numerator and a single thing in the denominator? What can I do? I can split into two different fractions, right?
So, yeah. 10x
Okay.
divided by 10. Plus
So, let's do that, okay?
Wait, what is it? Tangent plus cotangent, or tangent.
It's not gonna help us actually,
Cotangent.
okay? So we can stop right there and say, not gonna help. Alright,
Can you not
So-
just cross out on, within that fraction right there?
like what do you mean?
Can you not, like, it's just like, if you had 2 over 2, you can cross out and it turns into
Well,
1.
right, but it's plus.
Ah, yeah.
Okay.
For
So-
for the denominator, if you're multiplying tangent and cotangent together, isn't that just 1 anyway?
It is
oh,
just
but there's
one.
Y.
Oh, so somebody figured this out. This looks really super complex, doesn't it? Okay. But as George just pointed out, well, hold the phone here. If I multiply this together, wouldn't that be 1? But what's preventing us from doing that?
Y.
It's Y. Okay. So we got to take a step back again and be like, ugh, can't go further with that one. Okay. All right. Hold up 1 second here. Excuse me. What originally was written here in the book, let's see, I thought these was a typo and these are the wrong ones, but let's try what was originally written in the book. Let's see if we can do that. Okay, so what I'm going to go ahead and do is do the same sort of factoring thing I did before over here, okay, that I started to do. So tangent of x over tangent of x cotangent of y plus cotangent of y over tangent of x cotangent of y, like so. Any problem with what I just did there? Okay. What clearly will cancel it?
Tangent x.
Tangent of x.
On here the tangent of x is canceled. Over here the cotangent of y is canceled, right?
Yeah.
But that would give me 1 over cotangent of y plus 1 over tangent of x equals tangent of y plus cotangent of x. What's over 1 over cotangent? It's tangent, right? So this over here becomes tangent of y. And this one right there becomes
Cotangent of x.
cotangent. Which is equal to tangent of y plus cotangent of x. So, with this one, try not to get too bogged down with details. What I had done originally was I thought the book was misprinted, and that it was tangent of x plus cotangent of y, is what they meant. But looking at it again, I realized, nope, they were right. I was wrong.
Yes.
And now when you apply stuff, so seemingly you all had good ideas. Okay, you all tried different things, and it's just a matter of trying things out until you find the one that works. Okay, and so I mean, when you try something and it's wrong, it's quite clear quickly why it's wrong, or why it wouldn't work. So you try something, it's like, oh, that's not going to work. You stop, erase, go back, try again. Okay, try something else. And it may take you a few times before you find what it is, okay? And if after like a few times it's really becoming problematic, that's when you just switch everything to sine and cosine and try that, okay? But that's how this one comes out. Okay, good. Let's look at 39, okay? 39 looks absolutely ridiculous, doesn't it? Okay? It's 2 secant squared of x minus 2 secant squared of x sine squared of x, okay, minus sine squared of x minus cosine squared of x equals 1. Good Lord, that looks terrible, doesn't it? Okay? Actually not as bad as it seems. Okay? Alright. Which side do you think I ought to start with?
Left side.
The left side. Any reason why you think the left side?
More complicated.
Seems complicated.
It is clearly the more complicated side, isn't it? Okay? Clearly, yes. We want to start with the left side. Okay? However, there's a few other things that we can do here to this thing, okay? To kind of make life easy for us. Remember, we're allowed to make algebraic changes to these equations, okay? So, if I can, I should use algebra to my advantage to whittle things away, okay? The first thing I want to point out, okay, is that I've got a sine squared and cosine squared over here. What do we know about sine squared and cosine squared when they're put together? They always equal what? 1, right? Okay. Now here, it's normally sine squared plus cosine squared. But this is minus sine squared minus cosine squared. So what do you think it's actually going to be equal to? Negative 1. So I can make that substitution right there. Okay? And remember too, everybody, we could be completely wrong here.
Why can't you just cancel everything out?
What do you mean cancel everything out?
Well, some things are multiplied.
Some things are multiplying right there.
Oh.
So, can't do that. But, maybe, we try that first and say, oh, doesn't work. But I could make that a minus 1 equals 1, okay? Now, what can I do with the minus 1? I could bring it over, right, to the other side and make it 2. And that should probably be a good thing to do, right? Because what have I got on this side? Stupid 2 out in front of everything, correct? So what can I do that 2? I can factor it, right? I can factor that 2 out. Okay. Divide these both sides by 2. Okay. Now, almost done here. I'm actually almost done. I have secants on both sides. I have a secant in my equation. Right? Okay. Does the secant and the sine get paired together? Are the secant and sine ever paired together? No, right? So my option is I either want to get rid of the secant or I want to get rid of the sine. Okay. So which one do you think I ought to try to get rid of?
Sine?
I hear sine. Why sine, do you think?
Because it's in minority. I don't know.
Because it's a minority. There's more secants than there are sines, right? So perhaps it's easier to deal with getting rid of the sine than it is the secant, right? Now, what are ways I can get rid of the sine that help me out with the secant?
Negative.
Okay? What can I do with the sine? I can divide it out, okay? But if I did that, I'd have a secant squared over sine squared. That's not something I'm very comfortable with dealing with, okay? Because it's not something we've seen before, okay? But what else can I do?
Sine 1 over cosecant.
So the sine is 1 over the cosecant, right?
Yeah.
So maybe I should make that flip, shouldn't I? Then things are in terms of secants, okay? So if I did that, I'd have secant squared of x minus the secant squared of x over the cosecant squared of x equals 1. Secant over cosecant. What should that remind you of? Okay? It's what?
Tangent.
It's the tangent, right? And now I've got secant squared, tangent squared, and 1. What does that tell you that should be right there? What is that?
Pythagorean.
It's a Pythagorean identity, right? I can make it look exactly like the one in the sheet by just moving that tangent over, correct? Okay, so we can go ahead and do that. And that's a Pythagorean identity. Okay, and we're done. We don't have to go any further than that. So even though I didn't whittle this down to one thing, okay, if you could get it down to an identity to use over and over again, that's good enough. Because the identities we've already proven. We already know they work. So if I can show something is equal to one of those identities, I don't have to go any further. I mean, if I really wanted to be like super strict about this, I'd be like, okay, now we got some Pythagorean identity, so I can replace the 1 plus the tangent squared with secant squared, then both sides are secant squared. Okay? Or I can replace the secant squared with 1 plus tangent squared, and then both sides of that. You don't need to do that. Once you get it down to identity, you're good. Okay? But note how what we did here, okay, we started with something that was really super complex. Okay? That's about as nasty and as hard as they come. Okay? And just using algebra first, we work it down into something that's a little bit more manageable, and then we use our algebra, we use the trig identities to get it to show the equivalence. Okay? So, a lot of the times you do these things, it all goes back to basic algebra. Just cleaning things up so that way you can do it. Okay? Which is why we go all the way back to the first slide here today. The rules. Okay? Rule number 1 was just pick a side to start with. That's not that hard to do. You got 2 choices. Okay? Rule number 2, though, was do algebra stuff. Look for opportunities to do algebra stuff. So notice how that one has prioritized over using trig stuff. There's a reason for that. Okay? It's because 90% of the time, these things are just doing algebra. Okay? And so that's what I'm getting at here. Okay? All right. Any questions on how these work right here? Okay. We've got 10 minutes of class, and so I want to go over a few things so you're good for tomorrow. Okay? More identities. More. Actually, no, wait, no.
Less.
Lie.
Less.
Lie.
Less.
Lie.
Liar.
Not more identities. I was getting ahead of myself. So we got all those down. Now, why we do a lot of these trick stuff and shuffle things around, class, who is sleeping, half of you, is so that way we can actually solve trigonometric equations. Okay, that is, things where we want to find a solution for x. So, for example, if I said solve, okay, the sine of x plus root 2 equals minus sine of x. Okay, how would we go about doing that? Okay, the thing we wouldn't want to do is just start randomly plugging in values for x and see which one just happens to make this thing work. We want to be able to do something here to actually clean things up, don't we?
Yeah.
Okay, so we got to figure out kind of ways to go about doing it. Some of the obvious things we could do here. One obvious thing is what? Okay, move the sign over, right? Okay, because we don't want minus sign and sign. So I'm actually going to move this sign over, and the square root on the other side, okay? So get our trig thing by itself, basically. Okay? So move that over there, move that over there. And so we're gonna get 2 sine of x equals root x, okay? Now what can I do to both sides there?
Is it minus root x?
Oh, minus, yes it is. Thank you. Okay, now what can I do? Do I ever like having a 2 with the sign? No, we don't like having 2. So I'm going to divide both sides by 2. That means the sine of x then is equal to minus root x over 2. Okay? What can I do to that root? I want to get rid of the root, right?
Yeah.
So I could do what? I could square it, right? But if I square this side, I have to square this side. Okay? So if I do that, I would have sine squared of x is equal to x over 4. Any problems there? Okay? This is going to seem kind of crazy. I'm going to go ahead and move the x over 4 back over. Okay? Because then I'm going to have the sine squared of x minus x over 4 is equal to 0. Okay? Now, why on earth do you think I would have done that? What's that actually going to be equal to? That's a quadratic formula, right?
Wow.
Okay? So I could try to apply quadratic equations to it, okay? But there's something easier I can do here. I guess I could have done it in this first step right here, but I wanted to get it down to there, okay? When you have trouble, because it's still hard to kind of say, hey, how on earth am I going to figure out, basically...
Oh, foiling.
Oh, also too, I totally miswrote this problem, but that's okay. It was in the very beginning that was a square root of 2, not a square root of x, which totally changes the way you would approach this problem. But this is still a good exercise.
Yeah.
I could FOIL this, I could try to factor it, but at the end of the day, I'm still going to have sine of x minus x over something, or sine of x with x plus something, right? I'm going to still have all these x's, it's going to be hard to figure out. There's one way, though, I can always find an answer to one of these problems. Okay? One way. It always works. These things have a solution, it will find them for us.
Graph.
Graphing, yes. Bring up our friend the graphing calculator. And we would, there it goes. Okay? We go into our graph, and we graph what we've got. So we've got the sine of x squared. That's how you enter sine squared of x in your calculator, by the way. Okay. Notice how there's parentheses around the angle? That's so that way it doesn't read that as sine of x squared, but instead squares the whole sine. Okay? And we're going to subtract from it x over 4, correct? Okay? We go ahead and graph that. Okay? I'm probably in degrees. Yes, I'm most certainly in degrees.
Is that linear?
Huh?
Is that linear?
I'm sorry?
Is that a linear one?
No. It's because I'm in degrees, so the window is really big. You want to always be in radians for these problems. Okay. And as you can see here, the graph is doing its thing, it's wiggling around, coming close, crosses. So, if I zoomed in right here, I would say, oh, I've got a crossing point right there at 0. That one was easy. We saw that in the other graph. But I've got another one right there, don't I? Okay? Well, at some other location. Well, instead of trying to guess or zoom in with the calculator or something like that, tell the calculator, give me that location. The way you do it, right up here is a menu that says Calc. You bring that up. It'll ask you value, 0, minimum, maximum, intersect, and then some stuff for calculus. We're looking for a 0 in this case. So we choose 0. Okay? And so say left bound, that's just a point to the left of our 0. You could either scroll with this thing, okay, till you reach that point. Actually, there's a third crossing point that we didn't see. That's cool. There's there's totally a third one, somewhere very close to the origin. We'll look at that. We'll look for that one in a second. Okay, let's do the obvious one. So I can scroll until I'm at a good spot, hit enter, scroll until I'm beyond. and hit enter again, so come down here, and hit enter. And then guess is just where you think it crosses. Looks like it crosses about there. Hit enter. And totals our first 0, so we had a 0 at 0. So one solution was x equals 0, another one was x equals 2.285. Okay? And then as we were scrolling around, we discovered, hell, there's a third one, isn't there? Okay? So we can have the calculator find us the third one as well. The other way to find zeros is you can manually enter in numbers. Okay? So it was really close to 0, wasn't it? Like, so I'm going to put in like 0.001 for a left bound. Okay? That's a good enough left bound. Right bound, 1 should suffice. Okay? My guess, I don't know, guess is just wherever you think. You can scroll or just, you don't even have to guess, you just hit enter. Okay? And it's going to do its magic and find the location for you. And so there's another one at 0.256. Okay? And so there are all 3 of the solutions to this particular graph. Now you might be saying, well, Mr. Dowell, it's a quadratic equation. Don't they only have 2 solutions? Okay? Well, yes, but part of it was a what? Sine, right? What does sine do?
Undulates.
It undulates waves, right? So it's gonna, so if it crosses, it might even like wave around and have multiple crossing points. The second you throw trig into something, the standard rules of quadratics go out the window. You would have multiple answers, okay? In fact, you get so many answers that oftentimes the book will tell you, just give all the answers between 0 and 2 pi or something like that, okay? Because otherwise you're gonna have an infinite number of answers, and that's not really all that helpful, is it? Okay. But this is how you would approach doing one. Okay. Any questions? All right, good. So this is how you do it with the calculator. Otherwise, you just use regular algebra. In fact, if I was doing this problem normally, I'd use algebra to get it down. It's in the book. You just use algebra to get it down, and then solve it with the arc sign. That's what you are supposed to do. But this one got more difficult. Okay. So for tonight, you're going to have some problems trying to solve things. Basically, solve things for a value of x. When that comes up, if you have trouble, if you can't figure it out, use your calculator, okay, and just have it find the zeros for you, okay? The one thing, too, is sometimes they'll say find all the answers between certain endpoints. Go ahead and go into your calculator's window and enter those endpoints as your x minimum and maximum, okay? Get yourself a smidge of space, yeah. So if it's like from 0 to 2 pi, enter from like 0, like do like -1 to 3 pi or something like that, okay? Just to give you a better picture, okay? All right.
Smart.
Y'all have a good day.
Yeah, you just
Which is equal to x. So that way when I put the 2 functions together, I get x back down, okay? Now,